at section 4.2 on null spaces, column spaces, and linear transformations. So the null space is our m by n matrix A such that that is the set of all our solutions of our homogeneous equation of ax equals our zero vector, and it's in set notation saying the same thing, x such that x is in Rn, and ax equals our zero vector. So if we're looking at this set system of homogeneous equations, homogeneous because we have equals 0, then we can say in matrix form that ax equals 0, where A is the matrix of our coefficients. So let's figure out if U belongs in the null space of A. So U is 5, 3, negative 2. How can we figure out if U is in the null space of A? Pause the video, try it out. Well, if we have A times U equals our zero vector, then U is in our null space. So let's just do that really quick. What do we have for A? And then multiply by 5, 3, negative 2. And what do we get? We get 5 minus 9 plus 4, so that's 0. And negative 25 plus 18, no, plus 27 minus 2, which is also 0. Fantastic. So, yes, indeed, U is in null A. So U is in null A. This is the vector space chapter. Well, because the null space of an m by n matrix is a subspace of Rn. And the set of all solutions to our system, ax equals 0 of m homogeneous linear equations of n unknowns, is a subspace of Rn. So we're looking at vector spaces. In order to verify that this is a subspace, what do we need? We need our zero vector contained, we need closed under addition, and we need closed under scalar multiplication. So try to verify those. Zero vector is definitely in there, right? Because this trivial solution is going to be there, so that's okay. If you had AU plus V, is that going to be AU plus AV? Well, that's going to be our zero vector plus our zero vector, and so it's still going to work, so that's good. And then scalar multiplication, does that work? We have A times some times some scalar on U, but we can commute that, right? So we have A U multiplied by our scalar. So those are equal, and then this part is 0, so C times our zero vector, and that's going to give us 0, so we're good to go. Subspace is a set of all our vectors in R4, the 4 is important, whose coordinates A, B, C, and D satisfy the equation of A minus 2B plus 5C equals D, and C minus A equals B. How can we show that H is a subspace of R4? So we can make these two equations into our system of equations that's homogeneous by just moving that D over. So we got A minus 2B plus 5C minus D equals 0. And let's see, negative A minus B plus C equals 0. So if we have that, then we have a system of homogeneous linear equations. And so if we think back to theorem 2, then we have a subspace. Lovely. To find a spanning set for the null space of this matrix, pause the video and try it out. I'm going to use MATLAB. So never mind that I numbered this wrong. It's fine. So I have my matrix A, and then I made an augmented matrix A with a column of zeros, and so we're going to RF that and see what happens, and there we go. So we have our general solution that we can write from here. means that we have 1x1 minus 2x2s minus, what's that, 4? Minus x4 plus 3x5s, and that equals 0. And we also have x3 plus 2x4s minus 2x5s equals 0. And from here, we can write this as, let's see. So we can write this as x1 equals 2x2 minus plus x4 minus 3x5, and also x3 is negative 2x4s plus 2x5s, and x2, x4, and x5 are all free. Right? So we can rewrite this as, with our x1, x2, x3, x4, and x5, poorly spaced, but that's okay, with this expression for our x1, and then x2 is free, this expression for x3, and x4 and x5 there, and then we can break this up so that we can have the weights with we can write this in terms of weighted with our x2, x4, and x5. So we get 2, 1, and then we get zeros. x4 times the vector 1, 0, negative 2, 1, 0, coming from all the 4s that we have. And then x5, which is going to be multiplied by negative 3. There's no x5s in the second column. 2, 0, and 1. So now we have some vectors. We have vector, we can call this one u, call this one v, and call this one w. And so we can have our, we can express our null space as our linear combination of x2 times vector u as defined above, plus x4 times v, plus x5 times w. And that is our spanning set, is just our vectors u, v, and w, which are written right here. So that is our spanning set of our null space of A, which was given up here. I like that our spanning set of u, v, and w, it's linearly independent because we're looking at free variables that are the weights of our spanning vectors. And also we have our null space of A that contains non-zero vectors, and the number of our vectors in our spanning set for our null space is going to be equal to the number of free variables that we have. Because in order to get this spanning set, we had to use our free variables, and we had as many free variables as we ended up with in our spanning set, because that's how we got them. So those are a couple things to note. Alright, let's think about column spaces. M by N matrix A, it's written as column A, is the set of all of our linear combinations of our columns of A. So it's the all of the columns, just break it down. The column space of an M by N matrix A is a subspace of Rn. M. And that makes sense, right? Because we can't have it as a subspace of Rn, that we wouldn't have enough, we wouldn't necessarily have the same amounts of information. So it's a subspace of Rm. And our column space of an m by n matrix A is all of Rm if and only if the equation Ax equals b has a solution for each b. Oh, and I guess we should also be able to write this in our set notation. So column A is the set of b such that b equals Ax for some x in our n. So that's our set notation of defining what column space of A is. So try this out. Find a matrix A such that W equals column space of A with this. So pause the video, try it out. I mean, what we're looking at is just we have A times 6, 1, negative 7 plus B times negative 1, 1, 0. And that's about it. So we have the matrix A is just these columns put together. So we get 6, negative 1, 1, 1, and negative 7, 0. There we go. Matrix A, which is 3 by 4. If the column space of A is a subspace of Rk, what is K? And if the null space of A is a subspace of Rk, what is K? Pause the video. Alright, so the column space, looking at how big each column is, it's 3. So K equals 3. And looking at the null space, well, look how long each row is. It's 4, so K is 4. A lot more examples in the book, and you can definitely look at them. But we're going to briefly just look at this chart. So we have the null space of A and the column space of A. What's the difference? These are the differences. So null space is looking at Rn, column space is looking at Rm. Null space is implicitly defined, whereas column space is explicitly defined. You just read it off from the columns. It takes effort. You gotta do some row reduction in order to figure out null space. But column space is super simple. You just read off the columns. It's not necessarily obvious what your relationship between null space and your entries of A are, unless it's already in reduced row echelon form. But column space, you're just looking at the columns. Your typical vector in your null space gives you a solution for a homogeneous equation, where AV equals our 0 vector. But when you're looking at a vector in column space, then it has the property, it makes it so that AX equals V is going to be consistent, so it's going to be a solution. But it's not. But the V is not being multiplied by A. For figuring out if a vector is in the null space, just like our first example, you just multiply, and it's great. If you're looking at a specific vector and you're thinking about is it in the column space, then you need to do your row operations. So it's kind of like they're flipping. What's more complicated? In null space is going to be your 0 vector if and only if you only have your trivial solution. Your column space in Rm is equal to Rm if and only if we have a solution for every b in Rm. And null space is 0 vector if and only if we have 1-to-1, and column space equals Rm if and only if our linear transformation is onto. Thing, just kind of jumping off of that, tying everything back to linear transformations. So we have linear transformations as defined, remember from section 1.8 we were talking about this, where you have linear transformations, and we have addition and scalar multiplication not changing, right? So that's part of the definition of our linear transformation, and that looks remarkably similar to subspace stuff, so that's nice. But yeah, so our kernel, which is another way of saying our null space of linear transformation, is a set of all of your u's that get you to your zero vector, and then your range is happening from over here, where that's what you're getting to. And linear transformations, so if we have T as a matrix transformation, then the kernel and the range of T are the null space and the column space of A. So kernel is null space, range is column space. Alright, so that about does it. We looked at column space and null space. We did a lot of computation. We let MATLAB do it for us, and there we are. Alright, bye.